Hi, Ron Kerr here. I'm going to talk about 5D interpolation. 5D interpolation has become a fairly common procedure in land 3D seismic processing. And what it can do is it can improve signal to noise before the migration. And a lot of people think it's magic because it creates new traces where they did not. Now, it's applied after all of the pre-processing has been completed. So refraction statics, denoise, deconvolution, residual statics, more denoise, of course, and then it would be applied just before migration. Now, it's not applied on CDP gathers. You need to resort to common offset vector tiles, COV tiles, sometimes called offset vector tiles, OVTs. And what these are is they're common source, common receiver tiles across the 3D data set. So a common offset, maybe 1,000 to 1,200 meter range, and an azimuth, a source receiver azimuth of, say, 0 to 30 degrees azimuth. Once you sort everything, then you can infill with 5D interpolation. Why do you want to do it? Well, it can increase fold, and infill is missing offsets. So it's common with land 3D seismic surveys that you don't have complete coverage at all offsets everywhere. And 5D interpolation can help infill that. It can help the signal to noise. Just think of it this way: signal will interpolate, and random noise won't interpolate. So therefore, you're going to increase your signal to noise. You can also regularize the data to keep all of the offsets similar and all of the source receiver azimuths similar throughout the volume. That can help if you're doing azimuthal analysis for anisotropy parameters. Migration swings are common in Kirchhoff land surveys. Well, after 5D interpolation, you can have reduced migration swings. And that's because you have higher consistent fold everywhere. After 5D interpolation is complete, you have these populated tiles, COV or OVT tiles. You migrate those each tile individually for a pre-stack time or depth migration. Now, it's called 5D interpolation. It doesn't have to be 5 dimensions, but it can be 5 dimensions. And the reason it's called that is because you look in multiple dimensions to create a new trace. And it doesn't have to be, but a common 5 dimensions might be offset, azimuth, inline, crossline, and time. Now, I can only show examples that I draw by hand if nothing published, but if you look online, you can certainly see before-after gathers and before-after stacks. But this gives you the idea. So this might be a CDP gather before 5D interpolation. And notice I've got offset increases to the right, time goes down. Each vertical line here would be an individual trace, but notice there are gaps here where we have missing coverage, which is not unusual in 3D land 3D surveys. After 5D interpolation, we would have a much regular coverage like this. So for every offset azimuth increment, we would have an individually new trace. How would that look on a stack? Well, this might be your stack line before 5D interpolation. Time goes down. Our CDPs go from left to right. That might be an east-west direction. And if you look, there is might be a near-surface hole or skip. And these might be 3 reflectors down at depth. And you can see I have better coverage in areas, better continuity on these 3 reflectors in some places than others. Where it lines up is this skip is because we don't have any sources in that region. Maybe this is a small town. Maybe this is a highway or road, and we can't put sources there. So we're missing our near offsets. We don't get coverage till deeper in section. And because of that lower fold, we might have reduced continuity, worse signal to noise on these 3 reflectors under this area of lower fold because we cannot acquire data there. Now, outbound of it, where we have a more full fold area, we might image these reflectors just fine. Now, after 5D interpolation, we infill those traces on the gathers stack, and we get better results. We can have more consistent and improved signal to noise on these 3 reflectors at depth, And because we've added new near offsets, we can have interpolated coverage in between and get better reflectors in the shallow as well. Here's before 5D. This is keep the native traces. And here I've reduced all the two folds to one fold and put everything bin centered. Now, I'm not going to give an opinion which one I like. Some people like option 1, just the infill. Some people like option 2, plus regularization. A lot of it depends on your individual taste and the native geology. Maybe it reacts better to one than the other. Another way to look at this is in offset azimuth space. So let's assume our red star here is the source point. Our receivers are off the screen, beyond what we can see. So our midpoints are at the black dots, and our offset increases away from the red star along these circles, concentric circles, and our source receiver azimuth increases counterclockwise. So in several places I have 2 fold, some places I have 1 fold, some places I have 0 fold. And similar to the other example, this is after 5D interpolation, but this is with the infill or keep native traces. So I've kept these 2 where they are. Or I can do to option 2, regularize, and put everything right in the dead center. Oh. An example of how you have an infill versus regularized, but how complicated is it to write a new trace? Let's look at it this way. This is a graphic, and this is similar. This is one tile, one OVT tile, and let's assume I'm at approximately 2,500 meter source receiver offset, and plus or minus 30 degrees source receiver azimuth. You can see cross lines going this direction, inlines going this direction. Each inline cross line bin is a square, and I've colored the squares. The ones that are white are 0 fold. They have no midpoints in them. The ones that are a light gray are 1 fold. They have 1 trace in there. And the ones that are dark have more than 1 fold. So here's this empty bin. We want to write 1 new trace here at this inline, this cross line, at this inline, and at this cross line, and at this specific offset and azimuth. How do we write a new trace there? Well, first, let's look at neighboring traces right here. These have the same offset and azimuth and similar inlines and cross lines, so that this trace will probably be something like those. And we could stop there. That would be, looking in 2 directions, the inline and cross line direction, before writing it. And also, let's look at the same azimuth. These are the same plus minus 30 degree source receiver azimuth. Now we've got shorter offsets, and we've got farther offsets, so that would be at this location, but slightly nearer or farther offsets. We can look in those directions as well before writing that trace. Similar, we can have the same offset and inline and cross line, but let's look in the clockwise azimuth, let's look in the counterclockwise azimuth. We can look in all of those directions and time and before writing a new trace. And there we've written our 1 new trace. That's a lot of work just to write 1 trace. But we need to do this for all of these empty bins, for every inline, for every cross line, for every offset, for every azimuth. It's very complicated, it's very time consuming, but it helps. So in summary, 5D interpolation can improve signal to noise, partly because signal interpolates and random noise doesn't interpolate. We infill missing offsets and source receiver azimuths. Where there was no data before, we're writing new traces now. You can improve your velocity control because we've got higher signal to noise and we've got more fold coverage. It can reduce migration swings because we have more consistent coverage everywhere. And it can help preserve amplitudes because everything's consistent. Our fold is more consistent. Now, after we're done with 5D interpolation, then we would migrate these individual OVTs or COVs and pre-stack time migration for pre-stack depth migration. And if you want to see real data examples, they can certainly be found online, or you can take our course. And speaking of our course, I want you to be aware that I teach a 4-day professional seismic training course. This is me, Ron Kerr. Our course is called Understanding Seismic Data in Time, Depth, and Geology. We cover lots of real data, real world problems. It's a professional training course meant for today's interpreters, people who work with seismic data. You can reach out to me at this email address. I teach along with my colleagues, Dr. David Kessler and Dr. John Bird, and we cover all things. Dr. Kessler is more of a seismic theory and migration expert. Dr. Bird is more of a seismic interpreter and knows geology very, very well. And I teach a little bit of the processing. Thank you very much. I hope you learned a little bit more about 5D interpolation. I appreciate it.